So here we are moving on with a little bit more on Lewis structures, almost done, but today we've got to look at our exceptions and then just touch on a little bit on bond enthalpy. So up until this point, we have looked at Lewis dot structures that follow the octet rule. That is, that they have 8 electrons in their valence shell, so 8 electrons in the valence shell, okay, when they're stable, okay. So things such as if we look at carbon, when it forms with methane with 4 hydrogens, we can check in this case that carbon has 2, 4, 6, 8 electrons in its valence shell, so it's stable. But we can see straight away that here we have an exception, and that exception is hydrogen. Okay, so hydrogen is one of our exceptions in that it's stable with only 2 electrons in its valence shell. Okay, so we still follow the steps that we've looked at previously, looking at the total number of valence electrons, putting in lines or dots and crosses for our bonding, for our sharing to the central atom, and then making sure that each one is surrounded to complete the octet. In this case, this is where we need to take heed of our exceptions. So hydrogen requires only 2 electrons in its valence shell to be stable. Beryllium requires 4 electrons in its octet to be stable, which is why it's one of those weird ones that we looked at in ionic, in that beryllium should, in theory, be a metal and form ionic bonds when it bonds with nonmetals, but in the case of some nonmetals, in particular chlorine, it will form a covalent compound rather than an ionic compound. And even more weirdly, when it does that, if we look at this Lewis structure over here, we can see that beryllium has 2 electrons of its own, and then it forms 2 bonds sharing electrons with the chlorine, but that means that it only has 4 electrons in its valence shell. Chlorine's maintaining its octet with 8, but beryllium only has 4. Okay, and it's actually stable when it does that. The other exception that we need to pay attention to here is this one here, which is boron. And boron, straight away we can see, has 2, 4, 6 electrons. There's no lone pair up here. It does actually only have 6 electrons. It has 3 of its own in its valence shell, and then it will actually form 3 covalent bonds in this case. Okay, so boron has 6, beryllium has 4, and hydrogen has 2. There are, of course, as always, other exceptions, but these are the main ones that we need to know. Okay, so we can go through and we can form double bonds. Hopefully now you're feeling pretty confident about drawing Lewis structures. And remember that if we are dealing with an ion, we need to either add an electron to give it a negative charge, or if we're dealing with something that's positive charged, such as ammonium, okay, we're going to take that electron away. We would have 1 less electron if we were doing ammonium. Okay, so if we look at this, we now can move on to looking at structural formulae, okay, where we have replaced the shared electrons, this bonding pair of electrons. Okay, so this bonding pair has been replaced by a line. Okay, while this form here is valid, I do encourage you to instead draw it as Cl with Cl and then use the dots for your electrons rather than using these lines, because this can actually later on give us confusion in regards to molecular geometry or electron domain geometry. So I would recommend not drawing this way. We can still, as long as we are replacing bonding electrons with a line, then we're all okay. Okay, and then we can still show our lone pairs. When we're looking at structural formulae, they don't always show the lone pairs, but you should include them as a good idea. So if we've got 2 shared pairs of electrons, so more than 1 pair, we can have something such as oxygen. It only has 6 valence electrons, 2, 4, 6, so it will need to share 2. In this case, it will form a double bond. We then show that double bond again, and then just show our lone pairs like that. Okay, so it gives us a double covalent bond. Okay, so we have already actually done this, but if we draw a Lewis diagram of a molecule of nitrogen, nitrogen has 5 valence electrons, so that means it can form up to 3 bonds, so it will form 3 bonds. So now if I draw my Lewis structure, I'm going to put those in the middle, and then the lone pairs on the other side. Again, 2, 4, 6, 8. Each one is actually quite stable. So if we look at this now, if we replace those into a structural formula, we can see that we have a very strong triple bond here. So it's actually quite unreactive because it has a strong triple bond which is very, very stable, drawing the two nuclei close together, so it'll be hard to break apart. And whenever we have a chemical reaction occurring, we need to break these bonds, to break the bonds between the reactants and form new bonds with the products. So nitrogen is actually very unreactive because of this strong, stable triple covalent bond. Okay, so we refer to that as a triple covalent bond where it's sharing 3 electrons from each of the nitrogen